Section 10.8 is arc length and curvature. We'll split that into two parts. We'll do arc length and arc length parameterizations, and then we'll cover curvature in a second video. Now, the arc length of a differentiable function R is pretty familiar. It's similar to the case of two dimensions. We have L as the arc length. We'll take the derivative of our parameterized vector function R, so it's R prime of t. We'll take the magnitude of that and integrate from a to b with respect to t. And the formula looks very familiar to two dimensions, only now we have a z prime squared thrown in there. Now just to recall more or less where this formula comes from, if we're given a curve in 3D, a three-dimensional coordinate axes, and we want to add up the length from a to b, say here to here, we can do that approximately with line segments, as we've got these three line segments here. And the shorter we make the line segments, the closer we get to the actual value or the actual arc length. Of course, that's the limiting process that derives the integral here. But suffice it to say that that holds up as it normally would. Each of these li's is equal to the square root of, well, these portions here squared, with, of course, primes in there too. X prime squared, y prime squared, z prime squared. Okay, so for further details on our proof, the textbook would be a decent place to go. Now, from here, we'll just calculate arc length simply using the formula. We're asked to compute the length of the curve r of t equals 2t natural log of t squared along the interval 1 to 6. So that's just a direct application of the formula. Limits of integration are 1 to 6, r prime of t, magnitude, and we carry that out. Square root for the magnitude. This is the first component derivative squared, second component's derivative squared, derivative of the third component squared. So that sets us up. We're off and running. There's a point here where we need to factor out t to the negative 2. We factored it away in this step from 4 and t to the negative 2 to get these two pieces of two terms in this expression. Once that's done, we can factor this expression into this binomial squared. We have the square root of something squared, so those things cancel, and we end up with 2t squared plus 1 times t to the negative 1. Factor this t to the negative 1 through, and we arrive at, once we evaluate the limits of integration, the answer to this, the solution to this problem. So nice straightforward application of the arc length formula. Okay, so something more interesting we can do with arc length is use it to reparameterize curves so that they are arc length parameterized. In other words, they move at the speed of their own curve, or 1 to 1 for each point on the curve. Recall that parameterizations are not unique. If we have a parabola, y equals x squared, it can be parameterized in two dimensions as t comma t squared, or just as well t cubed comma t to the 6th. Now, either of those produces the same exact curve in two dimensions. The difference is the first one moves a little bit slower than the second one as t progresses from 0 to 1 or 1 to 2. So that's the interesting part of this. To get sort of a standard parameterization, we might call the arc length parameterization that standard parameterization. So the arc length parameterization is the function r of t such that r prime of t's magnitude is equal to 1. So the magnitude of the derivative of this vector function is 1. So for each step it takes along t moves from 1 to 2, then the distance that we move along this three-dimensional curve is exactly that 1 unit, or 2 to 3. Another unit covered is another unit distance along the curve. In order to do that, we're going to need to make use of the arc length function, which is just a measurement of the length of the arc r as we progress from a to the variable t, and tells us what distance we've traveled along this curve R. Okay, so we'll keep that function handy. Now there's quite a bit to this. Below is a derivation of this, the steps that we're going to use. I'll just use the steps that are condensed in a box on the next page. But the second part of this is the way we'll check things. Okay, so in other words, when we get our solution, it'll be this function right here, R1 prime of S without the magnitude. What we'll do is we'll want to take its magnitude and just double check that we get a value of 1. So to repeat that more clearly, R1 of S will be our solution. R1 prime is the derivative of our solution. Take the magnitude. That should be equal to 1 at all times. That will be the check for whether or not we got this correct. Okay, so let's see an example in which we work the steps out as listed above. 3 steps. Find the arc length function. Find the inverse function of that. That's pretty simple, usually algebraic. And then form the arc length parameterization by substituting that function of S in for every variable t you have in the original function. So the longest part is the first part, finding S of t using the formula. So we're given R of t is this vector function right here. So we're going to integrate from 0 to t, R prime of u du magnitude. So we need to take the derivative of this function to get 2, negative 2, 1. Square all 3 of those terms, as in this expression here, the magnitude bars, to get this integrand. This is just a constant, root 9, so we have 3. Finishing out that integral, we end up with S of t is equal to 3t. So pretty straightforward integration. We got lucky with this problem or this example. The next thing we do, collect this function here, and we need to invert s equals 3t. That's just an algebraic process. Solve for t. So we get t is equal to 1/3 s. Now that's phi of s. So whatever we solve for t, t and phi are essentially the same function. I'll write that off to the side. The phi off to the side, just to keep this clear as to who's who. So once we find phi of s, this is one of our last steps, we just rewrite our function r1 of s, we form it as our original function r, and we substitute for t our expression phi of s, in this case 1/3 s. So we see 1/3 s substituted for t into all the original variables of the function, t variables of the function, and simplifying the terms that show up from that gives us the function down below. And that more or less completes the solution to this problem. Now, if you want to check it, it's always a good idea, especially if you have time. Take the derivative of this function and then find the magnitude of the derivative function. When you do that, you have something that looks like this. You'll see that it's all equal to 1 and everything checks out. We found the arc length parameterization. Now to do one more that's a little bit less trivial than this one is the following. Find the arc length parameterization of the function r of t equals e to the t sine t, e to the t cosine t, and e to the t. So in this situation, we probably want to take the derivative first all by itself. Using the product rule, we obtain this expression here in terms of standard basis vectors. So there's r prime of t. We'll rewrite that as the dummy variable r prime of u, just for a variable of integration. When we substitute r prime of t for r prime of u and take the magnitude, we square the I, j, and k components of this vector function underneath that radical. Everything has a common factor of e to the 2u. We can factor that out of the radical as e to the u. Again, we're integrating from 0 to t. Just as in the problem before, if it's not specified where to start, we just assume 0 and integrate up to t. So next step is realizing that this term and this term are opposite sign from each other, so they add to 0 and cancel out. We have a value of 1 by the Pythagorean identity, another value of 1 by the same identity, and then we have a 1 in the very back of that radical. So we have 3 under the radical times e to the u. So our integral comes out to root 3 e to the u, evaluated from 0 to t, and that leaves us with root 3 e to the t minus e to the 0, which is 1. So there's s of t. To invert this, it requires a little bit of algebra and then the logarithmic function, and we end up with phi of s is equal to natural log of s over root 3 plus 1. Just taking steps to solve for e to the t and then take natural log of both sides. This is our phi of s function. What we do with it is plug it into our original r function to form r1, the arc length parameterization. We do so noting that e to the natural log cancels out to the argument of the natural log. And this is the finished product of this one. About as simple as it gets too. So that's it for arc length parameterization. In the next video, we'll finish up 10.8 with curvature.